Our next math topic that we're going to look at is called the Euler Phi function. Now, before we define what this function is, we're going to review what it means for integers to be relatively prime. Then we're going to review why integers being relatively prime has been important to us in certain contexts that we've seen before. We're then going to define what the Euler function is. We're going to compute some examples. And finally, we're going to find some nice alternative ways of computing phi of n for different values of n. Alright, so recall that what it means for two integers to be relatively prime is that their GCD is equal to 1. And this was important to us in a couple circumstances that we've seen. First of all, in simplifying fractions, that was really important. If you remember, if you had 8/12, we knew that wasn't simplified, in part because the GCD between the numerator and denominator, 8 and 12, is equal to 4. When we were able to reduce that to 2/3, we knew that one was simplified because the GCD of 2 and 3 was equal to 1. In other words, the numerator and denominator were relatively prime. In our class, when we were looking at certain ciphers, it was important to find multiplicative inverses of certain integers mod n. And when we did that, we discovered that an integer a has an inverse mod n precisely when the GCD of a and n is equal to 1. In other words, when a and n are relatively prime. So again, another example where being relatively prime was important to us. And actually, these are just two of many examples of when prime integers are important in an area of math we call number theory. And by number theory, I'm talking about the mathematics that involve the integers. Anyway, so now we're going to go ahead and define what the Euler Phi function is. But before we do that, we're going to ask a question. And so given an integer n, how many integers are actually relatively prime to n? Now, this question turns out not to be a very good question because the answer is infinitely many. There are infinitely many integers. It's pretty easy to manipulate those integers so that they're relatively prime to any number that we can imagine. And so that's maybe not the question that we want to ask. So an insight that we can lead us to a more interesting question is, well, once we know the numbers between 1 and n that are relatively prime with n, we actually can figure out all the rest. And let me show you an example of that with the number 6. So what are the numbers that are relatively prime with 6? Well, if we just look between 1 and 6, that's the first 6 integers, then you can see that 1 and 5 are the only ones, right? 2, 3, and 4 both share common factors with 6 besides 1. Now, if we look at the next 6 integers between 7 and 12, well, there you're just going to get 7 and 11, right? And if you look at the next 6 integers between 13 and 18, it turns out you just get 13 and 17. And actually, if you look carefully, you can see a pattern here, right? If you look at 1, 7, and 13, they are all multiples of 6 away from each other, right? 7 is 6 away from 1, and 13 is 2 times 6 away from 1. It's 12 away from 1. And same with the 5 and 11, they're 6 away, and 5 and 17, they're 12 away. So if you want to find all the numbers that are relatively prime with 6, they are going to look like 1 plus 6 times an integer and 5 plus 6 times an integer. Which means that if we can just figure out the numbers between 1 and 6 that are relatively prime with 6, then we can figure out all the rest. And that's true of any number n, not just 6. So now we can rephrase this question. Given an integer n, how many integers just between 1 and n are relatively prime with n? And that one gives us a more interesting answer, and we're going to give that answer by the Euler Phi function. So the Euler Phi is a function on the integers, which means the integers are inputs to phi. And the output of phi of n, where n is an integer, is the number of integers between 1 and n that are relatively prime with n. So if you imagine all the integers that are relatively prime with n and just count how many those are, that's exactly what phi of n is. So it tells us how many. All right, so here's some examples. So if we wanted to find, say, phi of 10, we're going to find some really slick ways of figuring this out. But right now, let's just sort of stick with very straightforward way. So the straightforward way we would do is look at all the numbers between 1 and 10, see if we can pick out all the ones that are relatively prime with 10, and then just count them. So if you look at the ones that are relatively prime, you can see that those are 1, 3, 7, and 9. So there are 4 of them that are relatively prime with 10, so that means phi of 10 is equal to 4. If we do something similar with 8, we look at all the numbers between 1 and 8, 1, 2, 3, 4, 5, 6, 7, 8. We look for the ones that are relatively prime with 8. That just turns out to be all the odd ones, rather. And then there are 4 of those. So again, phi of 8 is equal to 4. 4 seems to be a popular number. I wonder if they're all 4. No, probably not. Because if we look at phi of 7, we look at all the numbers 1, 2, 3, 4, 5, 6, 7, and it turns out almost everybody is relatively prime with 7, except for 7, of course. So there are 6 of those, which tells us that phi of 7 is equal to 6, not 4, right? All right, so now let's think a little more strategically about how we can compute phi of n. We have basically 2 main strategies. The first one you've seen. Look at all the numbers between 1 and n, figure out which ones are relatively prime with n, and total them up. These were fine with the examples that we saw, and in particular for small numbers where you don't have a lot of numbers between 1 and n. But in general, this is going to be pretty difficult to do. I mean, imagine trying to use this on like phi of 1,000, right? That I have to check 1,000 different numbers to see if they're relatively prime with 1,000. That can be kind of difficult. An alternative strategy, which turns out to have some real merit in a lot of cases, look at all the numbers between 1 and n, not the ones that are relatively prime with n, but specifically the ones that are not relatively prime with n. Total those up, and then subtract those from the total amount of numbers that you have. In other words, there are n numbers between 1 and n, so take the total numbers that are not relatively prime and subtract them. Now, computationally, this seems really twisted, but it turns out in most cases, this is generally less hard than finding the numbers that are actually relatively prime. And let's see if I can show you this in an example. So let's say we're trying to find phi of 27. Now in the old days, we'd look at all the numbers 1 through 27, figure out which ones that are relatively prime, and then count those up. Well, we're going to do the flip side of that problem, is we're going to count the numbers that are not relatively prime with 27. And that may sound kind of hard, but it's actually fairly easy, because if we factor 27, we get 3 times 3 times 3, right? 3 to the 3rd power. Which means that if we want to think about what the GCD of 27 in any number is going to be besides 1, it has to be a multiple of 3. Right? So we're going to be looking for multiples of 3. Those are going to be the numbers that are not relatively prime with 27. So how many multiples of 3 are there between 1 and 27? Well, that's not going to be hard at all, right? We look at 3 times 1, that's 3. 3 times 2, that is 6. 3 times 3, that is 9. 3 times 4 is 12. We keep on going until we get to the last multiple of 3, right before we get to, less than or equal to 27. And that's 3 times 9, right? 3 times 9 is equal to 27. So we have 3 times 1 through 3 times 9. All we have to do is count all those multiples of 3. The nice thing that we have here is that 3 times 1 through 3 times 9, that's 9 numbers, right? So we have 9 numbers that are multiples of 3 between 1 and 27, which means that if we want to find phi of 27, we subtract out those 9 numbers to get 18 numbers overall. And as you can see, that's a lot easier than trying to find all those 18 numbers that are relatively prime with 27. All right, so let's look at a slightly harder example. This is phi of 36, but we're going to use very much the same strategy. So now we're going to count the numbers that are not relatively prime with 36. And let's see. Well, this is going to be a little more complicated because if you see, when we do the prime factorization of 36, then what's going to happen is we are going to have we're going to have 2 prime factors. We have 2 to the 2 and 3 to the 2. And so now it's going to be a little bit more complicated because we are going to look for multiples of 2, and we're also going to have to look for multiples of 3 and take those all out and see what we have left. Okay. Again, this shouldn't be too bad, right? Multiples of 2, 2 times 1, 2 times 2, 2 times 3, all the way up to the last multiple of 2, and to get to 36, that's going to be 2 times 18, right? And if we count those, that is 18 numbers. All right, so now we do multiples of 3. We have 3 times 1, 3 times 2, 3 times 3, all the way up to the last multiple of 3. 3 times 12 gives us 36, so we get 3 times 12, and that gives us 12 numbers. And so we say, okay, yeah, there are 18 multiples of 2. There are 12 multiples of 3. That must mean there are 18 plus 12, which equals 30 multiples that are either multiples of 2 or multiples of 3. So are those all the non-relatively prime numbers? Well, the short answer is no. It turns out we counted too much. We counted too high. It's going to be less than 30. And the reason is, there are some numbers that were counted twice, right? There are actually some numbers that are both multiples of 3 and multiples of 2. And you can actually see them up there if you look closely. If you look across from the multiples of 2, we have 2 times 3. If you look across from the multiples of 3, we have 3 times 2. That got counted twice. So for instance, 6 got counted twice because it's a multiple of 2 and a multiple of 3. Also, 12 got counted twice because that's a multiple of 2 and a multiple of 3. Same with 18. It's a multiple of both 2 and 3. 24 and 30 and 36. So there are actually 6 numbers that got counted twice. So what do? Well, I mean, we could say, well, this is all messed up and we could just give up. Or we could say, look, those 6 numbers were counted twice, which means our total 18 plus 12 was just six numbers too high. So we can take that 18 plus 12, subtract out that 6 to rectify the count, and then we end up with 24 non-relatively prime numbers with 36. And then if we want to figure out the ones that are relatively prime, we take those 24 numbers and subtract them from 36, and we end up with 12. All right, so now I think you're ready to work on the class activities. The title of the PDF that you're going to see is the Euler Phi function.